Welcome everyone to the second in our CyberScholar webinar series coming to you from the TAC in Columbia, Maryland. I'm your host, Steve Hutchinson, Director of Research at the Technology Advancement Center, where we focus on cybersecurity projects, small business referrals, along with STEM and cyber workforce development. Our CyberScholar series of talks invites leaders from academia to inform us and discuss current hot topics in cybersecurity. Today's speaker is Justin Leiden from Texas A&M, who will talk to us about cyber physical systems in critical infrastructure. Justin Leiden is the Program Director of Operational Technology, Engineering, and Cybersecurity at the Texas A&M Cybersecurity Center. He's the designer and director of the Texas SCADA testbed, where his team designs industrial control and process control environments to meet workforce development needs, while also providing engineering support and materials for researchers. He's also program director for the Virtual Institutes for Cyber and Electromagnetic Spectrum, also called Viceroy. It is funded and managed by a partnership between the Air Force Research Lab and the Griffith Institute. Justin holds a Master of Science in Cybersecurity Operations from Mississippi State, an MBA from University of Mississippi, and will start a PhD in Computer Science at Texas A&M this fall. Like last time, Justin's talk will be presented in segments, 4 segments. At the end of each segment, I will review the Q&A questions and pose these individually for Justin's response. We will not use the chat feature, so please just type your questions as you get them pertaining to the current segment topic into the Q&A pop-up window. So let's begin. Over to you, Justin, for the first topic.
Thank you so much for that warm welcome. I'm super excited to be here today, and I'm really grateful for the platform. If you'll give me just a moment, I'm going to stop my video and share my screen. All right. As Steve was kind enough to say, my name is Justin Leiden. I'm the program director at Texas A&M University. I cover cyber physical systems engineering for workforce development and research needs, which has given me the tremendous experience of taking in people that don't know a whole lot about operational technology, training them to the point where they're able to contribute as engineers, and then mentor them. So my favorite part of this job by far is giving people the basics and the fundamentals. That's what I'm going to do with you guys today. So before we begin, I'd like to walk you guys through a bit of a thought experiment here. Close your eyes, and I want you to picture the first object that comes to mind when I say the word technology. Oddly enough for me, even though I work in cyber physical systems, the first thing that comes to my mind is an iPhone. My grandmother loves to print chain emails off still. It's 2024 and she still does that. And she mails those to me. So I would think that she would probably imagine a printer. My mom's a pharmacist, so she probably thinks of the desktop computer that she works on. But you might be thinking of supercomputers, quantum computers. If you're an engineer, you have a ThinkPad, some type of MacBook, an iPhone, or even the large language models that we've seen deployed more recently. Now, the reason that I bring this up today isn't to point out that cyber dominates our definition of technology, but to point to the fact that there are other components within technology that deserve to be defined within the word as well. To reinforce that point, here's a picture of what could be our great grandfather or mother. I'm not really sure which side we land on there. Holding the first piece of literally groundbreaking technology. We'll call it the iBone. And this is actually an image of Moonwatcher realizing that he no longer has the latest generation of the iBone. So the point of that is not to get you guys to laugh or call me a dork, which I'm sure I succeeded on both fronts there, but to reinforce the fact that until we start including cyber physical components that we might not include in the word technology in our definition of technology, we will never be able to protect it with the ferocity or comprehensiveness that we do our current cyber systems. All right, so into the meat and potatoes, IT against OT. Operational technology is a old technology, but a fairly recently defined domain. For those of you wondering where we draw the line between the two here, I used to just draw a manufacturing facility next to your traditional skyscraper / corporate office on a whiteboard and just draw a line right down the middle. And I would say, hey, here in this manufacturing facility, we have operational technology that's cyber physical systems involved. And here on the IT side, we have our data management distribution focused technology. And I guess about 4 or 5 presentations ago, this one guy raised his hand and was like, hey, well, what about the elevators in the corporate office? I was like, well, you got me there. So I typically try to break these down now by the process and data-centric focuses. So the professional way to answer the question, what separates the information technology that we all know and love already from operational technology, is that information technology focuses on data management, while operational technology focuses on process control. And when we say process control, we're talking about a cyber physical process. Some examples of operational technology that underpin our everyday life, even if we don't really recognize it, include industrial control systems, energy distribution equipment, engineering workstations, which for those of you not in the know, if you take a desktop computer and you put it inside a manufacturing facility, it magically becomes an engineering workstation. And industrial Internet of Things, which is a fairly new integration in operational technology. So let's go back to what I would say is the beginning, and that's going to bring us back to Motown. For those of you that aren't fans of R&B like myself, we'll just call it Detroit. Back in the first half of the 20th century, we began to use electricity. We used it to signal processes and give them information on when they should start and when they should stop, which is kind of like the foundation of automation. And this is what this image here is what we use to do that. It's commonly called an electrical relay panel. At the time, and this is like the 30s, 40s, and early 50s, this was groundbreaking technology. I mean, we were taking electricity for the first time and using it as a mechanism to start and stop physical processes, which was just, I mean, you gotta think about the technology that was surrounding you in the early 40s. So this is incredible stuff, but it had some very serious challenges associated with it. The first is that they were really, really difficult to develop and took a very long time to get up off the ground. So even if you had a greenfield project, and greenfield means that you have no barriers, you're completely free to develop at will, these things took at least several months to get up off the ground. And the second is that they were very difficult to modify in the face of changes to the process control. So let's say we get an innovation in one of our sensors and we want to bring in a different sensor to make accommodations to that innovation. We have to reprogram this, and reprogramming it means we are physically changing wires. So after 2 or 3 of those sessions, you get something that looks like, a bowl of pasta. So it's just very difficult to modify. So in 1969, General Motors released a request for vendor quotes for a device that would include recent digital innovations, thanks to the transistor, that would allow for a more effective control system. And that same year, Dick Morley, who's an absolute legend in operational technology, would design something he called the modular digital controller. Now, this is an image of Alan Bradley, an Alan Bradley PLC-5. And I show that, one, because it's really hard to get clear images of the Modicon, the original controller. And 2, because it's the very same design. And then 3, because it was actually Alan Bradley that came up with the name programmable logic controller. So the reason that I have it scaled down here, I know it's a lot smaller than the other 2 images, is that this is a true to scale picture here. So what we've done is we've taken all the capability that we had, and both of those images to the left, added about 1,000 times more effectiveness and shrunk it down to something that was neat and organized at the same time. So let's talk a bit about the design. When GM put it out, they were really cognizant of the fact that this was going to be put on manufacturing facility floors. They were actually great in instituting that as a design feature, because this would also end up in oil and natural gas environments outside. So the ruggedness was very, very critical. They also wanted it to be physically modular. It's very important, because if a piece breaks, you don't have to go in and pull out the whole entire PLC. You can actually just replace the component that was broken. And they needed it, obviously, to be programmable, so they didn't run into the same issues that you saw there on the left. So we can think of a PLC almost like a switchboard operator here. And we already had, if you will, we already had the switchboard there and the hardwired electrical relay panel, but we needed something that would allow us to reprogram it. So what Dick Morley did was he inserted, if you look at the switchboard operator here to the left, a CPU that would allow these input-output cards to be reprogrammed. So just to give you a quick walkthrough of what we're looking at here, for those of you that haven't seen a PLC before, PLCs are modular, which means they're made up of several components. If we look here on the very far left, we see a power supply. That power supply is critical because our control system is going to run off 24 volts of direct current. We use it because it's safer and it's more stable. And in order to get that, we have to convert the AC that's coming out of the wall or a power source at point of origin. So that converts us, that gives us the 24 volts of direct current that we need, and it sends that to the CPU, which is to the right of that. And then that CPU uses these input-output cards to send signals to addresses that are connected to wires in here. So the way that we would send commands to our quote-unquote switchboard operator is by loading the CPU with a language that we call ladder logic. Ladder logic is super, super cool. It's called a language by the IEC, which is a bit of a misnomer if you ask me, because it's more of a diagram than anything else. But it gives us the ability to assign addresses. If you look at the very top left up here, you see X001. So that's an address that's tied to a physical input on one of those input cards. And then if you look at the right here, you can see outs. And those are coils tied to the Y addresses, which are output cards. So what we have here is basic logic that says, hey, if somebody presses the button that's connected to X001, I want you to send power through. And if the red button is already pressed, then we're going to roll across that contact as well. And it's going to send power out to our green light. It's very simple, and everything that you see here is Boolean. We can do logic using memory registers as well, and those are 16-bit memory registers. So if we needed to assign a value that's going to come up later, we can do that also. This is really fundamental. Ladder logic, you can include things called function blocks as well if you need to do things like counters and timers. But for the purposes of our overview today, I think this is pretty sufficient. All right, so on to industrial control systems. I think the best way for us to do this is to build it kind of from the ground up here, if that's okay with you. To give you all a good idea of what an ICS is, let's look at the components from the ground up using something that we call the Purdue model. So we'll start at level 0, which is the process level. The 0th level of our industrial control system includes a technology that senses and moves equipment on the physical level. The primary equipment, typically conveyor belts, pumps, presses, valves, actuators in the form of motors or linear actuators. We have sensors that take signals from this particular process, and these are the sensors that send the signals to the PLC. The PLC takes those signals, digests them, and then sends them back to a number of what we call actuators. An actuator is anything that moves something. So a pump, a valve, a linear actuator. We have a DC motor down there. It's the muscles of the industrial control system, if you will. If you want to think of it like a central nervous system, it's a pretty good analogy. The sensors are like our fingertips, our ears and eyes, and then the actuators are like the muscles that bring everything together. Now the sensors here, they need somewhere to send the data, right? And the motors need something to command them. This image shows what could be thought of as an automation center on the floor, and shows what we call an industrial control cabinet. Now, the star of the show is this Siemens model PLC down here. This is a relatively late model PLC, which means it's fairly modern. And if you look a bit closer, you can see a number of devices that we call variable frequency drives, which are responsible for controlling motor functionality. We have a number of power supplies at the top right, which we use to relay. And though you can't see it, these plastic bars that run across the middle, they're just like gray plastic, serve as wiring houses so that we are able to keep everything organized without just having that bowl of pasta. So cable management is your thing. This is a good industry to be in. On the left side over there, you can see what we call contacts, and those are the back of physical push buttons. It's best practice to have emergency stops in all these systems because we have things like human arms that are in the loop, and if something happens, you really need to be able to stop that process ASAP. So we typically have some type of physical command inputs like push buttons. And this is just an image of what it would look like closed. And you can see the push buttons there on the right and a little bit of high level information there on the left. So when I was doing the rehearsal with Steve, he was kind enough to point out that it might be good to show you guys what it actually is like in scale. So if we were to walk into something like a utility plant or a large scale manufacturing facility, we would find a wide variety of sensors and actuators and a large number of these industrial control cabinets. And just to drive the point home here, what we just talked about, just to summarize it, we have sensors sending information up to our industrial control cabinets. Those industrial control cabinets digest that information, run it through their ladder logic code, and use that code to send commands back to the sensor or to the actuators. Another critical thing to discuss here is the fact that oftentimes these PLCs have code that integrates what we call tags. We call variables in operational technology tags instead of variables. They integrate tag values from other PLCs. So it's very important that we have communication between the PLCs as well. So we have 3 lines of communication here going at all times. So to show you guys the third level, which is the supervisory level, and just to recap, we have the 0th level, which is our process level. Then we have the 1st level, which is our control level. And then we have the 3rd level, which is our supervisory level. This is where we bring the human into the loop. So level 0 and 1 are your basic dumbed down automation, stuff that you really don't need a human in the loop on, stuff that you can walk away from and let it run. But what happens if a valve starts acting up, right? You need some type of human to respond to that particular scenario. So we have something called a human machine interface. And for you IT guys, I think you would probably call it a GUI, but in operational technology, we call it a human machine interface, typically just an HMI. This is a photo of a plant operator standing at a number of HMIs that represent the processes out there on the plant floor. I'll describe it in detail in this image here. So if we were standing in front of this particular image and we were responsible for looking at an HVAC industrial scaled system, this is going to give us information on everything that's going on, what the fan speeds are and what the sensors are reading. But it also gives us the ability to override by clicking on particular values. So if something happens and we need to respond to something we would call an alarm, we have the ability to come in and do that as a human operator. Now, this is a super nice HMI. I would be very, very impressed if we walked into a facility and found something like this. I honestly think we'd be much more likely to find something that looks like this here instead. I did a little spinny wheel just to drive home the fact that this is probably sitting on Windows XP. But yeah, so we have basic tank values and we have the pump values and start and stop options that we need to control this entire process. So this is where we aggregate all the information from all the PLCs. They're all kicking it up to this point right here. And it's presented in a digestible way for plant operators who might not be engineers to control. So just to drive it all home here, if we look at levels 0, 1, and 2, we have sensors and actuators connected to the actual conveyor belts and presses and pumps that are kicking information up to the PLCs, which are communicating to each other and sending information up to the HMI. And one other important thing to touch on is that the information doesn't stop at the HMI. It actually continues on to what we call a historian database management system. And a historian is responsible for giving people the information that they need to make sure that the processes are running at optimized efficiency and effectiveness. So just to put it all together, I really like this image. It's nice to use to walk through, actually assembling the components of a industrial control system. So you see down here on the plant floor, this very, very flat, large level here, a number of conveyor belts and what are probably presses and a few pumps. This is where our sensors and actuators are going to fit. And these are going to kick information over to this wall. We have a number of industrial control cabinets over here. They're likely housing a number of PLCs and some components that are responsible for programming the motors here. And then that information is going to get kicked up to what we call the upper deck. So if you're standing on the operator level, it's typically called the upper deck in a manufacturing facility. And you can see here we have a number of displays, and we can, for the purposes of today, use our imagination and say that there's some HMIs on there. This image is particularly nice because we have a third floor up here, or a second floor if you're a computer scientist. And we can imagine that we have some C-suite operators up here and basically draw the line between OT and IT right here, this interstices between the first and second, or second and third floors, depending on how you define it. Okay, so I hear SCADA a lot. That's a really common term. I was actually hired as the Texas A&M SCADA program director, and I've worked really hard to educate people on this since I've been here. I actually changed my job title, which is at Texas A&M, HR takes a long time and stuff, so I was very impressed with the fact that I was able to get that done. But industrial control systems they're a common cyber physical system within the technology domain of operational technology. So we have operational technology, and within OT, we have industrial control systems. And industrial control systems can be thought of in the same way that we think of automobile. They're a general technology type that includes several different types of specific types of technology. Supervisory control and data acquisition systems, that's the one that we just walked through and built together. Supervisory control and data acquisition systems are typically just called SCADA, and they offer you two main functionality components. The first is the supervisory control, which we put together all the way up to the HMI. So if your PLCs connected to sensors and actuators, kicking information up to an HMI. And then the data acquisition, that's a big component with SCADA, because that data acquisition, as we saw earlier, that data is being sent to a historian time management database. It allows these guys that we call business analysts to come in and basically run statistical analyses to make sure that we're operating at peak efficiency. But SCADA isn't the only industrial control system out there. If you're looking at an energy distribution system, like your power grid, it probably uses something called an EMS, which in this particular case stands for Energy Management System. Distributed control systems are really nice as well. That just stands for DCS. It's very similar to a SCADA system, a bit larger scale, but without the data acquisition component. Typically, you take a number of distributed control systems and link them together within a SCADA control system. You also have safety instrumented systems. If you guys are, if you can think back to the Trisis attack, it was an attack on a safety instrumented system, hence the SIS in the name there. And these all in their most base form serve as a central nervous system for some type of cyber physical process. Down here are some names that you guys have probably seen. You might not be familiar with those. Siemens is a massive player in this particular field. They have almost all of the European market. Allen Bradley there in the middle dominates most of the domestic market here. ABB is a big player. Hitachi and Honeywell are all in the market as well. All right, so this time I'm going to pause for any questions that you might have up to where we're at.
Right, so let's see, we have a couple questions here. Maybe talk about the scope of how big an industrial control systems can get, maybe
Okay.
in different domains, power or.
Sure, yeah, okay. That's a great question. We can have a standalone PLC in a very small manufacturing facility that's connected to sensors and actuators that is defined an industrial control system. So one single PLC connected to some inputs and outputs would be sufficient, and our definition of industrial control systems. But they can get very, very large scale as well. Colonial Pipeline, we'll talk a little bit about them in the future. They have a number of networks that are all aggregated, and they stretch from, if memory serves, from at least North Carolina all the way down to Texas. So very, very large and expansive networks. A medium size control system, a great example of that would be a municipality's traffic grid. You're going to have a number of PLCs that are responsible for controlling a number of intersections that are all aggregated together and kicked up to a centralized SCADA system that a human operator works on.
Excellent. And one last one for this segment. Must an industrial control system use only PLCs? Are there some other technologies out there?
That's a good question. So programmable logic controllers are by far the most common used digital controller. But there is a very closely related controller called a remote terminal unit. The difference here is that RTUs are much better when you're placing a controller in a distance that isn't really close to another controller. So oil and natural gas pipelines use remote terminal units quite often. Another benefit with the RTUs, for the operator at least, is some of them come loaded with programming. They're a little bit easier if you haven't integrated a controller before as well. So very closely related, but we do define those particular types of controllers as remote terminal units.
Very, very good. Let's move on to the next segment.
All right. All right, so some cyber physical nuances. For the portion of our talk today, I'd like to present some of the more interesting operational technology nuances with cybersecurity implications. I'm sure that I'm going to leave a lot out, so hopefully if you guys have some questions, it'll give me a chance to address anything that I missed. There are so many things that differentiate operational technology from information technology when it comes to cybersecurity that it's really impossible to cover in the scope of this one single presentation, but I will cover the highlights here. The first thing that you need to consider is the number of operators. So we showed you that HMI earlier, and it's on a plant floor. Dollars to donuts can promise you that the guy that's sitting in front of that HMI is not an operational technology engineer. He's a plant operator, and he's one of many plant operators, which means that those screens that are holding HMIs at any given time have to stay up while operators are shifting switches or shifting their shifts, excuse me. So that creates some credentialing issues, right? So in information technology, we strive for the CIA bit, and if you expand it just a little bit to include non-repudiation, that can't be done without a set of unique credentials for each operator. And in operational technology, that's not really something that you have the ability to issue because you have so many operators at any given time on one particular system. So it's a good segue into the CIA prioritization of tenants. In operational technology, we kind of turn it on its head. It's fair to say you can prioritize the tenants in information technology by going C to A or C to I to A. But in operational technology, you can't really prioritize it like that because A and I, the accessibility and integrity, are critical. Yet you're running at a speed where you have to have virtually zero latency. So your accessibility is insanely important. But it's not more or less important than the integrity is, because if you're getting data that's coming in and isn't completely accurate, your process isn't going to run the way it's supposed to. Now, if we have those two stacked on top of each other or holding hand in hand, like we can go like 2 or 3 blocks behind and we find confidentiality way, way, way back. There's just not a whole lot of space for it on the process or control levels because that information has to be exchanged so quickly. When you find your way into like the SCADA level, especially the enterprise level, which sits above the SCADA, yeah, there's definitely room for confidentiality. But in my opinion, there's a lot of room for improvement in this particular tenant. And I think that's a fairly common assessment. It's just a really difficult challenge to integrate because you have to find some way to do that without slowing the latency down. We also have a really wide range of protocols. And Steve and I decided today that we're going to open up a brewery, and we're going to use a manufacturing facility for it. One of the first things that we're going to do is get some process control engineers to come in and help us design the automation system. And the second thing is we're going to need some engineers to come in and meet the automation guys and design a control system. And those guys are probably going to have a preference on their industrial control system equipment that they use. I'm a huge fan of Beckhoff myself. They're a very popular controller. But let's say the guy that comes in initially is a big fan of Siemens. There are a number of proprietary protocols produced like by manufacturers like Siemens that will essentially put you in a position where you have to continue to buy the equipment. And the way they do that is through creating their own proprietary protocols. So on top of the really expansive number of like open source field bus protocols, you also have a large number of proprietary protocols. If you look up operational protocols, I think that Wikipedia has 99 listed. They did at least about a year ago. So there's quite a few. In IT, you have the benefit of using the primary set of a handful of tops, but we have no such luxury in operational technology. Going back to that first point, the HMI operator is almost not it's almost certainly not a operational technology engineer. And so this ends up creating some challenges for the people on site there. The first is that we need to patch our equipment regularly. And if you don't have somebody that's familiar with interfacing with the equipment itself, it's difficult to do that. That creates another problem for us. And we'll talk a little bit more about this in the next slide or the slide after that, but we are supposed to be air gapping. The best practice is to air gap our operational technology network from our information technology network. And if you have somebody on the plant floor responsible for patching but doesn't know how to do it themselves, they are going to find a way to jump that air gap so they can have the OEM come in and do the patching for them. And you would be shocked at the scale of systems that actually do this. I mean, we have very large energy manufacturers here in Texas doing this exact thing. And we have a bunch who are following extremely good practices as well. But I've seen this on energy distribution facility floors. And then enabled but unused features. The SCADA software that comes out now, it's just absolutely breathtaking what they can do. It's really, really cool. The problem is that they give you a wide number of features that often don't end up being used. And if you don't have somebody that's interfacing with the system every day, they're not going to be able to identify when a functionality that might have offered initially just isn't being used enough to justify having it open anymore. And those of you that know, a function is a doorway, basically. Any feature that you leave open ends up creating the doorway that expands your attack surface. And then this one is really interesting. I haven't heard anybody else talk about this, but I've noticed this over the past 4 or 5 years at conferences. There's a huge cultural divide in information technology and operational technology. And I like the hard hat versus hoodie just because those are all words that start with H. But if you go into a plant floor, infrastructural or industrial, you're going to find operators wearing high visibility vests and hard hats. And they follow the same culture that you would expect that personality type to follow. And they don't typically see themselves as cyber operators. They don't see themselves as your typical hoodie and glasses working, 8 p.m. to 4 a.m. type person, which leads to this culture of disownership over cybersecurity, right? If you identify with cyber, you tend to take ownership of the security of that cyber. And if you don't identify as a cyber operator, it's just as easy to disown that particular responsibility. The cost of updating is a very serious consideration in operational technology as well. The equipment is very expensive, but not prohibitive. But the licensing is often prohibitive. You can easily spend upwards of $100,000 on equipment alone, and then have to spend an additional $70,000 to $80,000 in licensing. Engineering is expensive because you have to bring in engineers to pull the whole entire central nervous system out of the facility and install another one. Granted, there are overhauls that don't require complete removal and complete reinstallation. But it's still a very, very expensive process because in either complete or partial reinstallation, you have to turn your operations off. And that's the ultimate cost for a manufacturing facility, the downtime that is required to install new equipment and make sure that your hardware and software is patched and non-vulnerable. which leads to legacy hardware and software in our infrastructure and industrial environments. So we go back to the initial design features: rugged, modular, reprogrammable. We take these added up, we get a really, it's impossible to overstate how really long the life cycle of this equipment is. So we have a ton of legacy PLC models out there in the market right now, a lot. Most PLCs, when they were being integrated in the 70s and 80s, they did not come with the ability to do any credentialing. And then some models that came in after that that did have credentials were installed by people that didn't really think that they needed to change them in the first place. So a shockingly large number of our industrial control systems driven process control environments are accessible to anybody with access to the internet. That's a bit scary. They're also not typically capable of logging. The older legacy models aren't. Some of the newer ones are much better about it. But for those of you familiar with cybersecurity, logging is a fundamental function that you're going to use. And if you don't have the ability to log, it's really difficult to see changes that might throw alarms. And then all PLC models, and this one is super cool, all PLC models feature the ability to read programming from the PLC. And that's really important on an operational level, because if Steve installs a PLC initially, and if Steve installs a PLC and then I have to come in and work on it after him, I have to know what's on that PLC. I can't just reprogram the system. I have to be able to read the ladder logic that's on there. So let's say you're designing an attack that you will use to spoof a SCADA system in order to do something like overspin centrifuges, which is something that happened that we'll talk about in a bit as well. You have to have the addresses. And in order to do that, you have to have the programming. So you could take a laptop in, what the example everybody uses is just wear a high visibility vest and take a ladder in with you. And if you do that and plug it into one of the PLCs, which nobody is going to be alarmed by because most of these PLCs are worked on by guys who are contractors, then you can get those addresses that you need to do the spoofing that you need to make that attack a success. And then custom-made control systems are often stuck on obsolete operating systems. So if you look at this image down here of this HMI, you can tell that it was custom built for a process control environment with 3 tanks. And you can tell where the valves are, you can tell where the piping is. And it's important to note that this was built for that environment because it means that somebody came in at the time that this operating system was the standard, and on top of that operating system built this particular process control program, which means that you can't just update your operating system at any given point. So you end up with a lot of obsolete operating systems running modern process control systems. And then I got a little image of Clippy here because I did like some parts of the Windows XP. All right, so a couple last points on the cyber physical nuances. Failure to consider cyber physical security at ICS install. Those of you that are trivia fans, I'll give you a freebie here. The word cybersecurity wasn't in any dictionary until 1989. It wasn't until Nirvana was playing together that we saw the word cybersecurity even defined. And that led to a lot of flat architecture being installed at the point of install. We'll talk about this more in a minute, but you really do need to have some type of air gap or at least DMZ between these two systems. Over here on the left, you can see you have your IT assets. And over here on the right, you can see you have your engineering workstations and PLCs. So there's kind of a line right here between the middle that divides IT and OT. And at the time, nobody was really thinking of cybersecurity. So this is a really popular type of architecture out there right now. And then our infrastructure is heavily integrated or interconnected. That's because we have to have power to run most of our process control facilities. So you end up with a power distribution plant that's connected to a power generation plant. That power generation plant goes through the distribution plant to a series of transformers that distribute power to our traffic grid, our water treatment systems, our water distribution even. So you end up with the potential for what we call cascading failures. And that's problematic because it would be hyperbolic to say that in this case where you're only as strong as your weakest link, because there's definitely redundancy, but it's still worth stating that you have to make accommodations for the systems that you're connected to, because you can't always count on that redundancy. All right, so another pause for questions here.
Thanks, Justin. Just a couple. Is there any way of estimating the quantity, the number of legacy control systems out there?
In short, no. Yeah, so we have a staggeringly low amount of insight into the industrial control systems and the industrial control systems hardware that underpins not just our private industry. And the private side makes sense, right? Because I'm not going to share my specs if I have a manufacturing facility. I don't want that to be public knowledge, not with anybody, not with the government, right? But when you have public systems that are being underpinned by this cyber physical infrastructure, you really need some type of asset inventory. And in order to protect equipment, you have to know it's there. And we really don't have that as a nation. So it's really difficult to tell exactly how many pieces of legacy hardware software we have out there right now. But it's something that we should be working on.
What could we do about it? As a national directive, what could be the next step that we should be taking to close this security gap in critical infrastructure?
If I had complete control, or Congress called me one day and was like, "Hey, Justin, we need you to come and tell us what we need to do." My recommendation would be to do a national asset inventory on, at the very least, all the systems that are connected or affiliated with our critical infrastructure. And critical infrastructure, it's 16 sectors divided by this, defined by the Cybersecurity and Infrastructure Security Agency, a subset of Homeland Security. And we really need to do that, because all these security recommendations that are being made, they're not only as good as like the access to the information that you have at any given point. And we really don't have any type of finger on the pulse in terms of what kind of equipment is out there right now.
Scary. Thanks.
Yeah, I don't want to scare you. Most of this is okay, though,
On to the next segment.
Okay. All right, OT security standards. Earlier, we used this model to build our industrial control system from the 0th up to the 2nd level. I won't spend too much time on this, but the Purdue model back in the early 90s, a researcher at Purdue spent some time putting together what we would call secure architecture for networks that have enterprise networks and operational technology networks combined. And enterprise is another way of saying information technology network that's affiliated with some type of organization. So here, these top 2 levels, we have our enterprise and network. And the breakthrough with the Purdue model was they said, hey, we need to divide this into 2 sections, basically. We need our operational technology down here below a demilitarized zone. And we're going to take some firewalls and do some server mirroring and create this DMZ up here. And then above that, we're going to put our IT network. And by doing that, we keep attackers from being able to jump in through our information technology network, which is much more easily accessible, and installing any type of ransomware on our operational technology system or overspinning things and causing physical damage. This is a fairly old model now. Like I said, it was developed back in the early 90s, but it still remains a critical component in the security approach in operational technology, let's put it that way. It doesn't have a whole lot of favorable sentiment right now, because the industrial information, industrial Internet of Things devices coming into the operational technology level kind of turns it on its head. If you're going to have information technology associated equipment in your operational technology network, the Purdue model stops being effective in its entirety. We have 2 really popular security standards in operational technology. The first is the ISA 62443. This is a security standard and certification process that was developed by the ISA 99. That's the International Society of Automation Engineers. Really fantastic crew of subject matter experts that have a ton of aggregated experience in automation engineering. It comes with really strong technical depth, but it focuses with a tighter scope than the NIST security standard that we'll talk about here in just a moment. Because of that, we have this really large international adoption. Manufacturing exists all over the world, and the 62443 is a fantastic security standard. So it's been adopted pretty heavily internationally. One thing that separates the 62443 from NIST is that they kind of presented this idea of having zones in your architecture. And what zones do is they give you the ability to segment technology in a way that reduces your attack surface. NIST, the 882, we're on revision 3 now. The one big advantage that I see the 62443 having is that it came from industrial insiders in its entirety. It was nothing but a support of subject matter expertise, whereas NIST is a standards organization that covers a wide expanse of technology. To their credit, they did bring in industry insiders such as Rob Lee. And for those of you not familiar with that name, he's the CEO of Dragos, probably the world's leader in incident response and operational technology. Absolute legend in our field, and he has a wide breadth of experience prior to starting Dragos as well. But this set of standards is really good for policymakers. If you don't have any experience in operational technology and you need to give yourself some insight into it to make some policy, the 882 is a good way to go for that. A bit more high level, but in that level, you're able to include infrastructure and industrial processes. It's far more domestic in its integration, which makes a lot of sense since it's NIST, but another important piece to note is that it isn't a certifications pipeline like the 62443 is. They do, though, offer certifications for excellence. And I've been to one of the power companies. We have one here in Texas that has been awarded a NIST excellence cert through what seems like a very intense audit. And I can tell you they were zipped up. I mean, they might have power failures due to outdated equipment, but this one particular energy organization, it's not going down because it's being attacked. I can tell you that much. So some common threads, if we were to boil both of these standards down, as well as the Purdue model, and the Purdue model is featured, it's a note in both of those. Some common threads that you're going to find is air gapping is going to be recommended. It's really hard to do this because it creates a lot of disruption in your process, but it is the security gold standard. Keeping yourself from being accessible by the internet will keep you from being attacked. It is inconvenient, again, and in the face of IIoT, it's ineffective. So zero trust architecture is a really popular thing in operational technology as well. One-way communication is very effective, very effective. And then whitelisting instead of blacklisting. And for those of you unfamiliar with those terms, whitelisting is we have a pre-designated list of identification information that is allowed to cross our barriers. Instead of blacklisting, which is we have a pre-identified list of people that aren't allowed and everything else can come in, right? Because blacklisting at least the potential for something that's not identified as a problem to still slip through. Microsegmentation is probably the leading answer to the question, how do we protect our legacy hardware and software from modern attacks? And what microsegmentation is, in short, is creating a bunch of little segments within your operational technology network that are separated by firewalls. And what that does is it allows us to minimize our attack surface in the same way that you see this Navy aircraft carrier door. You see it's watertight, and that's because if we have a breach, we need to shut this door and keep the water just isolated to that one particular area, which protects the rest of our quote unquote network here. All right, another question break.
Very good. So you mentioned NIST doesn't really do certification, but 62443 does. What would a certification process typically look like for 62443?
Great question. So one thing that I'm especially excited to see in the 62443 is that there's two certification paths. The first is for an organization. You can get your organization certified through the 62443. Or if you're an operator and you want to get certified as a single operator, there's a certification path for that as well. Both of those processes begin at the isa.org website.
Very good. Let's go on to the next segment.
All right. All right, some notable incidents here. The last quarter of 2010, this is an incident most of the people on this call probably remember. The NATAN's nuclear facility went down through the work of what we know was Israel and what we suspect was the United States of America. The US has not claimed attribution, and I want to drive that point home. I'm not saying, Justin Leiden is not saying that the US was involved in that. I will say that there are a population of people who suspect that. So Steve and I decide that we want to build a nuclear bomb. The first step is going to be to get the materials that we need. And you typically use uranium for it, and that's because uranium, there's a lot of uranium in the world. The problem is that when you extract uranium, you get two isotopes. You get 235 and you get 238. And 235 is way more fissionable. So you want to separate 235 from 238. And the way you do that is you put them into these centrifuges and you spin them around. And NATAN's back in 2010 was enriching a lot of uranium, which is problematic because NATAN's was an Iranian nuclear facility. So what Stuxnet did was, it's a masterpiece. It came in and it targeted step 7, which is a Siemens piece of software. And through that targeting of step 7 was able to work its way only into the Siemens controllers, which were responsible for the centrifuges. When it got into those controllers, it spoofed signals from the sensors and to the actuators, from spoof signals from the PLCs to the SCADA system, and then from the SCADA system to the actuators. And what it did was it told SCADA, hey, everything's okay from the sensors. We're reading nothing but fine signals here. And it sent overspin commands to the centrifuges, which caused it to spin up a little too fast and destroyed not the uranium, because you can pull the uranium out, but it destroyed the centrifuges. And to this day, it's still suspected to be the costliest cyber attack of all time. And I love this example. I love it because it is such a poster child for the effect that you can have by just releasing a cyber attack into a cyber physical system. 150 lines of code. To this day, still one of the largest pieces of malware. And it was created through a operation called the Operation Olympic Games. And a couple power grid examples. I listed 2 here just to show you that you can have power grid failures from malicious activity, and you can have power grid failures from accidents. And both of those are completely natural. Oh, that's not true. One of those is completely natural. One of those is completely intentional. So the Ukrainian power grid, we've seen Russia and Ukraine kind of at odds for the past 2 years. But for those of you that have been paying attention internationally, they have been in a bit of a Cold War for much longer than they have these past 2 years. One offensive attack that Russia did was they brought the Ukrainian power grid down using a Trojan horse in 2015 and 2016. This single attack took hundreds of thousands of homes off of the power grid. And I'm a big fan of displaying this attack also because this is not a typo. This power grid provider over here on the right side, that's actually the name of the Ukrainian power grid that was taken down. Excellent sophistication. The advanced persistent threat was titled Sandworm. And then the Texas power grid failure in 2021 is another fantastic example because it shows that not all attacks are intentional. We just had failed. I'm from Texas. I'm in Idaho right now, but back in Texas, we simply failed to winterize our equipment. And this is just physical energy generation equipment. And because of our short-sightedness on that particular front, as winters have gotten colder in Texas, we've seen power failures in those energy distribution centers. because of the cascading failure potential that we discussed earlier, we saw something like 2.13 million individuals just in the Houston area alone lose access to power, which is just absolutely insane. Something that's notable is that Texas doesn't see cold weather all that often. And during the freeze, it was 13 degrees Fahrenheit for 2 days straight. And that's the 2 days that people lost power. So if you can imagine somebody that's used to 100 degrees for over 120 days of the year, feeling 13 degrees Fahrenheit for the first time, and then feeling it without power, that's a tough experience. And then Colonial Pipeline's a relatively recent one. This is a great example of the interdependency between information technology and operational technology, because DarkSide, who was the APT that facilitated this particular ransomware attack, they didn't attack the operational technology side. They attacked the information technology side. So they got in on IT and they threw ransomware, locked everything down, and that created a complete opaqueness over the operational technology network that the operators could not bypass. So they had two choices. They could either continue operating their facilities blindly, which would lead to a ton of unsafe situations, or they could shut down their operational technology network until their information technology network was back online and they could see what was going on the OT side. And they chose, in my opinion, the right thing to do. They shut things down until they got things back up. But just to show how disruptive this can be, this is the Colonial Pipeline, and it distributes gas all along this particular stretch here. There's no one single point where it comes out. So it was very, very disruptive. DarkSide, another really fun thing to point out is they actually made a public statement. It fell short of an official apology, but they publicly stated that it didn't fall within their mission statement to disrupt people's daily lives, that they were just after financial gain. So in short, they apologized without actually saying sorry for it. The FBI did recover quite a bit of the Bitcoins. I think it was like 74 Bitcoins or 64 Bitcoins were recovered. And then if you're interested in learning more, which is something I highly recommend, our friends at the Cybersecurity and Infrastructure Security Agency have come up with a free asynchronous training platform that offers a ton of really, really cool classes. I came up through Idaho National Lab, and something that I'm really proud of is their work with CISA. CISA has an Idaho Falls location as well, and they do a lot of collaboration. One of the things that they've collaborated on are these classes, and one that I would recommend kicking off with is the ICS 301V Industrial Control Systems Cybersecurity course. It's completely free, it's totally asynchronous, and it's virtual. So you're able to, at your own pace, over a period of 2 weeks, go through this series of modules that give you what they describe as a mile wide but an inch deep introspective into operational technology cybersecurity. And at the end of it, you get a continuing education unit and you get a certification for completing the course. Some additional reading sources that I highly recommend: the NIST 882. It's lengthy, it's a big document, but there are a ton of synopses out there, so I'd recommend looking into that. The ISA has a lot of good publications if you're not going to do the 62443. And then Dragos, our good incident response operational technology friends, and probably the most respected operational technology firm in existence. They do a lot of educational outreach, and part of that is presenting publications on their website. And then lastly, if you're in bed at 11 a.m. and you can't sleep and you decide you want to go to YouTube, RealPars has some fantastic reductions of operational technology concepts presented as YouTube videos. And so I can't recommend them highly enough as well. Like back in 17, when I was getting into it, that was the main source of information that I used. And then just to drive the point home, I mean, you cannot move throughout your day without touching some component that is underpinned by a critical infrastructure, industrial control system. I have epilepsy, I have to take a medication. That medication is generated through a chemical manufacturing facility that has an industrial control system in it. You turn on your lights, that power is distributed through an industrial control system. Every piece of product that you have that was involved in manufacturing touched it. You turn on your car if you're not driving electric. You rely on the energy refineries, and you turn on your faucet, the water comes out. That's also connected to an industrial control system. So it's hard to overstate how important it is for us to protect these systems. And I think the first step in protecting the systems is to get the information out there and say, hey, these are part of the cyber infrastructure that we need to be considering when we hit the point that cybersecurity needs to be integrated. When we drive that point home, we need to include cyber physical systems within the same definition. I think that's time. I'm pretty sure I'm basically right at an hour here. This is my contact information. I've got a QR code there. If you'd like to scan that, my contact information will go directly into your phone. And then I figured I would leave, one more question break here. If you guys have anything that's come along throughout the presentation, I'd be happy to address that. If not, thank you so much for having me today.
From the TAC, I'm Steve Hutchinson saying so long for now.